$40 billion. That is the estimated price tag for Russia's integrated air defense network. Decades of engineering, thousands of radar arrays spread across 11 time zones, the S-300 family, the S-400 Triumph, the S-500 Prometei, the Nebo-M counter-stealth radar, layer upon layer of electromagnetic coverage designed to track and kill anything that flies through Russian airspace. $40 billion to build a wall of radio waves so dense that no aircraft on Earth should be able to slip through. And then, in December of 2005, the United States Air Force quietly activated a jet that turned that entire wall into a suggestion. From certain angles, the F-22 Raptor has a radar cross-section of 0.0001 square meters. That is equivalent to the radar reflection of a steel marble, not a fighter jet. Not even a bird. A marble. A tiny sphere of metal about 1 centimeter across. Now try to picture this. You are sitting behind the most advanced radar console Russia has ever produced. Your screen is glowing green. You are scanning hundreds of kilometers of sky, and somewhere out there, moving at 1,500 kilometers per hour, is a 19-meter-long twin-engine fighter jet with a wingspan the length of a school bus. And on your screen, it is indistinguishable from a raindrop, from a bug, from nothing. That is the engineering reality that keeps Russian air defense planners awake at night. Imagine you have a mirror the size of a barn door. You aim a spotlight at it. The reflection is blinding, obvious, unmistakable. That mirror is a conventional fighter. Now replace that barn door with a piece of black velvet, and cut into a shape that scatters light in every direction except back at you. That velvet is the F-22. Same sky, same spotlight, completely different result. Russia built the spotlight. America built the velvet. This is the engineering that made it all useless. Let us break it down. Before we get into it, if you are the kind of person who watches a 30-minute engineering breakdown instead of a 3-minute highlight reel, you are our kind of viewer. Hit subscribe if you have not already. Tap the bell so you never miss a Weapons Lab video. And drop a comment telling us where you are watching from. We read every single one. Now let us get technical. To understand why the F-22 is so devastating to Russian radar, you first have to understand how radar works in the first place. And I mean really understand it, not the textbook version. More the physical reality. Radar stands for radio detection and ranging. The concept is elegant. You fire a pulse of electromagnetic energy into the sky. That pulse travels outward at the speed of light, which is roughly 300 million meters per second. When that pulse hits an object, some of that energy bounces back. Your antenna catches the return signal, and by measuring the time delay between the outgoing pulse and the incoming echo, you can calculate how far away the object is. That might sound simple, it is not. The energy does not just bounce back like a tennis ball off a wall. It scatters, in every direction. The amount that returns to your antenna depends on a staggering number of variables. The size of the target, its shape, the material it is made of, the angle at which the radar wave hits it. Now, the frequency of the radar wave itself. Every single one of these factors changes the equation. And it is an equation, literally. The radar range equation is the fundamental law of detection. Here is the plain English version. The detection range of a radar system depends on how much power you pump out, how big and sensitive your antenna is, the wavelength you are broadcasting on, and the size of the electromagnetic reflection your target produces. That reflection is called the radar cross-section, or RCS. Now here's where it gets interesting. The relationship between RCS and detection range is not linear. It follows a fourth root law. That means if you want to double the detection range against a given target, you do not need twice the radar power. You need 16 times the power. 16. In %, if the target reduces its RCS by a factor of 10, the radar does not lose 10% of its range. It loses about 44%. Think about that for a second. A relatively modest reduction in RCS causes an enormous collapse in detection range. This is the mathematical foundation upon which all of stealth aviation is built. The B-52 Stratofortress has an RCS as large as 100 square meters. It shows up on radar like a flying apartment building. Against a powerful search radar like the kind Russia operates, a B-52 is visible from well over 400 kilometers away. There is no sneaking a B-52 anywhere. A fourth-generation fighter like the F-16 has an RCS of around 5 square meters, and the F-15 has an RCS of roughly 25 square meters. Still very visible. Still very trackable. Still very shootable. The F-22's front aspect RCS is estimated at 0.0001 square meters. That is 50,000 times smaller than the F-16. 50,000. Against the same radar, the F-22's detection range collapses to a tiny fraction of what it would be against a conventional fighter. The S-400's panoramic radar has a declared targeting range of 340 kilometers against a target with an RCS of 4 square meters. That is roughly the signature of a large conventional fighter. Now apply the fourth root scaling to a target with an RCS of 0.0001 square meters. The math is devastating. The detection range crumbles to somewhere between 20 and 50 kilometers, depending on atmospheric conditions and electronic warfare. Reducing the frontal RCS of the F-22 to that estimated value makes it virtually undetectable at distances less than 30 to 50 kilometers in the best-case scenario. And by that point, the F-22 has already fired its weapons and is turning away. Now let us talk about how Russia actually operates these systems. The S-400 Triumph is a mobile surface-to-air missile system developed in the 1990s by Russia's NPO Almaz as an upgrade to the S-300 family. It uses multiple radar arrays operating across different frequency bands to detect, track, and engage targets. The S-400's radar system combines 3 different arrays that broadcast on various frequency bands to track, target, and locate aircraft. Russia has spent decades building one of the world's most extensive integrated air defense networks. And the newest element of that architecture is the S-500 Prometei. According to Russian officials, the system can track and engage stealth aircraft, hypersonic weapons, ballistic missiles, and low-orbit satellites. Those are the claims. But claims and physics do not always agree, and physics always wins. Now we need to go deep into the concept that makes or breaks every stealth aircraft ever designed. Radar cross-section, RCS. This single number defines whether a pilot lives or dies, whether a $40 billion radar network works or does not, whether an air force controls the sky or merely watches it. A radar cross-section is a measure of reflectivity, expressed in square meters, often generalized from the return from the head-on and level radar illumination of the airplane's nose. A complex mathematical formula converts that return to an estimate of the size of a sphere that would return the same measure of energy. So when we say the F-22 has an RCS of 0.0001 square meters, we are saying that to a radar, it reflects the same amount of energy as a perfectly conducting metal sphere, with a cross-sectional area of 1/10,000th of a square meter. 1 square centimeter. A marble. RCS is not a fixed number for any aircraft. It changes constantly depending on the angle of observation, the frequency of the radar, and the specific aspect the radar is viewing. An aircraft might have an extremely low RCS from the front, but a significantly higher one from the side or rear. The RCS value is a restrictive measurement of the aircraft's frontal or side area from the perspective of a static radar. Now, when an aircraft maneuvers, it exposes a completely different set of angles and surface area, potentially increasing radar observability. This is the part most people get wrong. They see a single RCS number and think it applies everywhere. It does not. The F-22's front aspect RCS in X-band is estimated at 0.0001 square meters, while the side and rear aspects range from 0.01 to 0.001 square meters. Even from the worst angles, that is still staggeringly small, but the front aspect is where the engineering is most concentrated, because that is the direction you fly toward the threat. How does shape determine RCS? It comes down to how electromagnetic waves behave when they hit a surface. When a radar wave strikes a flat surface at a perpendicular angle, it bounces straight back to the transmitter like a ball thrown against a wall. This is called specular reflection, and it produces an enormous radar return. A single flat plate 1 meter square, oriented perpendicular to a radar beam, can produce an RCS of hundreds or even thousands of square meters at typical radar frequencies. One flat plate, bigger than an entire aircraft. This is why perpendicular surfaces are absolutely catastrophic for stealth. A conventional aircraft is full of them. The vertical tail fin, flat engine faces, right-angle joints between the wing and fuselage, weapons pylons sticking straight out from the wing. Every one of these features acts like a tiny mirror, reflecting energy directly back to the radar. Now think about what happens if you tilt that surface. Then angle it just 5 degrees off perpendicular, and the specular return drops dramatically because the reflected energy is now directed away from the transmitter. Angle it 20 degrees, and the return collapses. Angle it 42 degrees, and it is effectively invisible from the front. The F-22's clipped diamond-like delta wings have leading edges swept at 42 degrees. That number is not arbitrary. It is not aesthetic. It is the result of millions of hours of computational electromagnetic simulation. 42 degrees was the optimal sweep angle that balanced aerodynamic performance at supersonic speeds, with the need to deflect radar energy away from the threat direction. And here is the engineering decision that ties it all together. Planform and panel edges on the F-22 are aligned to reduce the aircraft's radar cross-section. Every edge on the aircraft is aligned to one of a very small number of specific angles: the leading edges of both wings, the trailing edges, the horizontal stabilizers, the edges of the weapons bay doors, the edges of the access panels, every single one. Why? Because every edge on an aircraft is a source of radar return through a phenomenon called edge diffraction. When a radar wave hits the edge of a surface, it diffracts, meaning it scatters energy in predictable directions. By aligning all edges to the same angles, the F-22 concentrates all of its diffracted energy into a very small number of narrow spikes, rather than scattering it in every direction. This means there are a handful of specific angles where the aircraft produces a momentary flash of radar return, and every other angle is virtually silent. Yet a conventional aircraft scatters energy everywhere. The F-22 scatters it in controlled narrow beams that a radar is unlikely to be pointed directly into, like concentrating all the sound in a room into a single narrow beam that only hits one corner. Step out of that corner and you hear nothing. Let me give you the comparison in human terms. An F-16 has an RCS of 5 square meters. An F-15 has an RCS of 25 square meters. The F-35 Lightning II has an estimated RCS of around 0.001 square meters. The B-2 Spirit is estimated at approximately 0.1 square meters, and the F-22 sits at the bottom of this hierarchy at 0.0001 square meters. The radar cross-section of the F-22 is smaller than that of a bird, much smaller than that of any conventional fighter, and 100 to 1,000 times smaller than that of an F-16 or F-15. Its signature is so small that it practically blends in with the electromagnetic background noise. Think about that. The F-22 does not just reduce its radar return, it buries it in the noise floor of the radar receiver itself. The radar cannot distinguish the F-22 from the random electromagnetic fluctuations of the atmosphere. Now let me explain how frequency band changes the picture, because this is where the Russian counter-argument lives. RCS is frequency dependent. The stealth shaping and coatings on the F-22 are optimized for the higher frequency bands, specifically the X-band, C-band, and S-band, which are the frequencies used by fire control radars. These are the radars that actually guide missiles to a target. At longer wavelengths, such as those in VHF and L-band, stealth optimizations degrade because the aircraft's dimensions approach or exceed the wavelength, inducing resonant scattering effects that elevate RCS independently of shaping. This is the resonance problem. When the wavelength of the radar is comparable to the physical dimensions of the aircraft, the entire airframe acts like an antenna, re-radiating energy regardless of how cleverly it is shaped. We will come back to this problem in detail when we discuss the Nebo-M. Edge diffraction does not stop at the edges themselves. Electromagnetic energy that hits an edge creates traveling waves, surface currents that propagate along the skin of the aircraft, and re-radiate energy as they reach other discontinuities like joints, gaps, or surface changes. Reducing these traveling waves requires precise surface treatments, specialized coatings, and meticulous attention to every seam and fastener on the aircraft. The F-22 addresses this with a combination of radar-absorbent material, edge alignment, and surface continuity that is, to this day, the most advanced of any operational fighter. The fact that a 62-foot-long aircraft carrying internal weapons, a powerful radar, and 2 massive turbofan engines can present a radar signature smaller than a marble is, honestly, one of the most remarkable achievements in the history of engineering, not just military engineering. Engineering, period. Now let us talk about the invisible skin, the coating that absorbs radar waves before they can ever bounce back. Radar-absorbent material, or RAM. If airframe shaping is the foundation of stealth, RAM is the finish work, the precision detail, the final layer that takes an already low radar signature and pushes it into territory that makes radar operators question their equipment. Shaping of the object contributes the majority, nearly 80%, to the electromagnetic signature reduction, and the remaining 20% is achieved by using RAM and radar-absorbent structures. 20% might not sound like much, but remember the fourth root law. Every additional reduction in RCS pushes the detection range down. That 20% is the difference between being detected at 40 kilometers and being detected at 25. In aerial combat, that gap is life or death. So how does RAM actually work? Think of noise-canceling headphones. When you put them on, they do not block sound with a physical barrier. They detect the incoming sound wave and generate an inverted wave that destructively interferes with the original. The two waves cancel each other out, and you hear silence. RAM operates on a similar principle, but for electromagnetic waves instead of sound waves. The coating is designed so that when radar energy enters it, the wave interacts with the material in a way that converts the electromagnetic energy into heat. The wave goes in, and instead of bouncing back out, it is absorbed, dissipated, and converted into a trivial amount of thermal energy. Most often, RAMs comprising ferromagnetic particles dispersed in a polymer of high dielectric constant are used for effective stealth application. The most frequently utilized RAM is iron ball paint, which is based on tiny iron spheres coated with carbonyl iron or magnetic ferrite suspended in an epoxy resin. When electromagnetic radiation falls on the painted surface, it interacts with the iron ball paint and gets absorbed by the carbonyl iron or ferrite molecules due to their oscillation. Iron ball paint. That is the literal name. Microscopic spheres of iron, coated in carbonyl iron, floating in a resin. When a radar wave hits this material, the ferrite particles oscillate at the frequency of the incoming wave. That oscillation converts electromagnetic energy into heat through magnetic hysteresis loss. The radar wave is not reflected. It is eaten alive by billions of tiny iron spheres vibrating in unison. The SR-71 Blackbird employed a type of RAM known as iron ball, containing molecules of carbonyl iron ferrite. When that was the 1960s, the F-22's coatings are generations beyond that, incorporating not just traditional ferrite absorbers, but advanced composite materials with engineered electromagnetic properties. The F-22 has numerous layers of coatings applied to the aircraft skin. The initial requirements were for 3 layers of coating stacked together. The first coating is a primer designed to smooth and seal the surface of the skin and promote adhesion. The second is a conductive coating consisting of silver flakes mixed with polyurethane materials, intended to conduct, dissipate, and reflect radar waves away. The third is a top coat with other metallic materials and infrared properties to reduce heat and radar detection. In addition, other coatings such as radar-absorbent materials, gap fillers, and adhesives were applied on various specific areas, multiple layers, each one doing something different. The primer creates a smooth foundation. The conductive layer with silver flakes handles one aspect of the electromagnetic spectrum. The top coat handles another. And then on top of all that, specific areas get additional specialized coatings tuned to the particular radar frequencies those areas are most likely to encounter. The F-22 first gets a base coat of radar-absorbent or deflective materials, over which is applied a top coat developed by Boeing to counter a broad range of wavelengths, including infrared. So it is not just radar they are worried about. The coating also reduces infrared signature, making it harder for heat-seeking systems to track the aircraft. And here's the thing. This coating is a nightmare to maintain. And all this takes a lot of work to maintain, and many of these applications start degrading shortly after they are applied, with friction from high-speed flight, crushing G-forces, and the elements accelerating that process. Early coatings failed against rain and moisture when F-22s were initially posted to Guam in 2009. Stealth measures account for almost 1/3 of maintenance, with coatings being particularly demanding. 1/3 of all maintenance on the F-22 is dedicated to keeping its stealthy skin intact. That is an astonishing number. The highly engineered coatings cost around $1,000 per gallon, And you need a lot of gallons. Recoating inlets manually requires maintenance workers to wear protective suits and respirators and spend hundreds of hours crawling around on their hands and knees inside of them. And under those conditions, it is nearly impossible for workers to manually apply the coatings at consistent speeds and thicknesses. Since 2016, the Air Force has been using robots from Aerobotics to handle these chores. Robots. Because human hands are not precise enough to apply stealth coating evenly across serpentine engine inlets. Let that sink in. The tolerances are so tight that the United States Air Force had to build custom robots just to paint the inside of an air intake. Maintenance hours per flight hour improved from 30 early on to 10.5 by 2009. 30 hours of maintenance for every 1 hour of flight, 30 to 1. Even at 10.5 to 1, which is where they eventually got it, that is an extraordinary commitment of resources. This is the part Russia cannot replicate. And not the shape. Shapes can be measured and copied. It is the material science, the exact formulations, the layering, the application techniques, the manufacturing precision required to apply coatings within tolerances measured in microns across an entire airframe. The most classified technology in a stealthy airplane is its skin. That single sentence from Smithsonian tells you everything about where the real advantage lives. The Su-57, Russia's attempt at a fifth-generation stealth fighter, uses ram coatings, but independent analysts estimate its RCS to be between 10 and 100 times larger than the F-22's, depending on the aspect angle. The materials are not as advanced, the application is not as precise, the integration with the airframe is not as seamless. Stealth is not just about putting special paint on a jet. It is about every single system on the aircraft working together at the molecular level to defeat electromagnetic detection. Now let us go back in time and talk about where all of this began. Because the F-22 did not emerge from nothing. It is the descendant of a program so secret that even its name was classified for decades. In the mid-1970s, a small team at Lockheed's legendary Skunk Works division started working on a project called Have Blue. The goal was audacious. Build an aircraft that could penetrate the most heavily defended airspace on Earth, Soviet airspace, and do it not through speed, not through altitude, not through electronic jamming, but through a completely new approach. Make the aircraft invisible to radar. The Have Blue prototypes were small, strange-looking aircraft covered in flat, angled panels. The F-117 Nighthawk was the world's first stealthy aircraft, composed of flat panels, each angled so that no one is likely to be at a right angle to a radar. The F-117 was a master of deflection. The design philosophy was called faceting. Every surface was a flat panel tilted at a precise angle to bounce radar energy away from the transmitter. It worked remarkably well, but the aerodynamic penalty was severe. The F-117 flew like a brick with aspirations. It needed constant computer corrections just to stay in the air. The F-22 took a fundamentally different approach. The F-22's stealth technology was a revolutionary generational leap over the F-117, moving beyond a specialized stealth bomber to the first fully integrated stealth fighter concept. Instead of flat facets, the F-22 uses continuous curves, non-compound curves that smoothly transition from one surface to the next, each one precisely calculated to scatter radar energy in controlled directions. The F-22 proved that a highly maneuverable, supersonic fighter could also be extremely stealthy. Stealth became an integrated design element rather than a bolted-on feature that compromised aerodynamic performance. And that changes everything. The F-117 sacrificed flight performance for stealth. The F-22 demanded both. And somehow Lockheed Martin delivered. The leading-edge sweep of 42 degrees was not just about radar deflection. It also optimized supersonic lift-to-drag ratio, allowing the aircraft to supercruise, meaning sustained supersonic flight without afterburner, which itself reduces infrared signature. Every design choice served multiple masters: stealth, aerodynamics, and thermodynamics, all balanced against each other. Measures to reduce RCS include airframe shaping such as alignment of edges and continuous curvature of surfaces, internal carriage of weapons, fixed geometry serpentine inlet ducts, and curved vanes that prevent line of sight of the engine fan faces and turbines from any exterior view. The serpentine air intakes deserve their own explanation. Imagine trying to see around a curved hallway. You stand at one end and look in. The hallway bends in the middle and you cannot see what is at the other end. That is exactly what the F-22's air intakes do. They curve in an S shape so that radar energy entering the intake cannot reach the engine fan face. The fan face of a jet engine is one of the most reflective components on any aircraft. Thousands of spinning metal blades, perfectly angled to catch and return radar energy. It is essentially a rotating radar reflector. By hiding it behind a curved duct, the F-22 eliminates one of the largest sources of radar return on any conventional fighter. The alignment of edges, continuous curves, diamond-shaped flaps, tapered contours, the application of area rule and serpentine air intakes with S-ducts conceal internal components such as the engine fan. And then there is the canopy. The cockpit of any fighter is a cavity filled with radar reflective equipment, metal instruments, helmet visors, ejection seat mechanisms. Every one of these produces a radar return. The F-22 solves this with a gold-doped canopy coating. A microscopically thin layer of gold is embedded in the polycarbonate canopy. This layer is electrically conductive, turning the canopy into a smooth, continuous radar-reflecting surface that matches the impedance of the surrounding airframe. The radar energy never penetrates the canopy. It slides off the surface and is directed away, just like every other surface on the aircraft. Attention to detail such as hinges and pilot helmets that could provide a radar return is addressed in the F-22's design. Hinges. They worried about the radar return from hinges. That is the level of obsession that produces a 0.0001 square meter cross-section. The team extensively used analytical and empirical methods, including computational fluid dynamics, computer-aided design, wind tunnel testing of 18,000 hours, and radar cross-section calculations and pole testing. 18,000 hours of wind tunnel testing for one aircraft. And that was just the aerodynamics. The electromagnetic testing ran alongside it, with full-scale radar cross-section measurement on outdoor ranges using precisely calibrated equipment. Now I want to hear from you. Do you think radar technology will ever fully defeat stealth? Or has the F-22 proven that shaping and materials will always stay one step ahead of detection? This is a real debate happening right now in defense circles around the world, and there is no clear answer. Drop your take in the comments. And if you are enjoying this deep dive, share it with someone who would appreciate it. Let us keep going. Now let us talk about why the F-22 carries its weapons inside. Because external weapons do not just add drag, they destroy stealth. A missile hanging from a pylon under the wing is a radar nightmare. It is a cylinder with fins. It has right-angle junctions where it meets the pylon. The pylon itself is a flat slab of metal hanging perpendicular to the radar wave. Every external weapon adds square meters to the aircraft's RCS, not fractions, square meters. An F-16 loaded with a full combat configuration of external weapons, missiles, fuel tanks, and targeting pods can have an RCS several times larger than its clean airframe value. All those hard edges, all those perpendicular surfaces, all those cavity returns between the weapons and the wing, they light up on radar like a Christmas tree. The F-22 solves this with 3 internal weapons bays. The main bay is located in the belly of the aircraft, roughly 5 meters long. Although designed for air-to-air missiles, the main bay can replace 4 launchers with 2 bomb racks that can each carry 1,000-pound or 4 250-pound bombs for a total of 2,000 pounds of air-to-surface ordnance. In the air-to-air configuration, it carries 6 AIM-120 advanced medium-range air-to-air missiles, known as AMRAAMs. 2 additional side bays each carry 1 AIM-9 Sidewinder heat-seeking missile, 6 medium-range radar-guided missiles, and 2 short-range infrared missiles, all hidden inside the airframe. 0 external signature. When it is time to fire, the weapons bay doors open. And this is where the engineering is almost artistic in its precision. The bay doors open for less than 1 second per missile launch, less than 1 second. The missile is ejected using a hydraulic launcher that pushes it clear of the aircraft. When the doors snap shut, the window of increased RCS is so brief that most radar systems cannot complete a tracking update in that time. And even the doors themselves are designed for stealth. The edges of the weapons bay doors are serrated, sawtooth patterns along the edges that break up radar reflections and align the diffracted energy with the same controlled angles as the rest of the airframe. Nothing is left to chance. Every edge, every gap, every joint is treated as a potential radar reflector and engineered accordingly. Weapons are stored inside closed internal bays, except during launch, which significantly reduces reflective surfaces. This is not a minor detail. This is the entire operational concept. The F-22 goes into combat completely clean. No external stores, no pylons, no pods. Just a smooth, continuous outer mold line that presents the smallest possible radar signature from every direction. Compare that to an F-16 on a combat mission. External fuel tanks, targeting pod, 4 or 6 missiles, electronic warfare pod. The F-16 is a capable aircraft, no question. But it announces its presence to every radar within 300 kilometers. The F-22 slides through the same airspace like a ghost. While the F-22 typically carries weapons internally, the wings include 4 hardpoints, each rated to handle 5,000 pounds. The hardpoints are there for non-stealth missions where maximum payload matters more than invisibility. But in a contested environment, against advanced air defenses, those hardpoints stay empty. Now we arrive at the confrontation that this entire video has been building toward. The F-22 versus Russian radar systems. Theory against practice. Engineering against engineering. Billions of dollars of radar investment against billions of dollars of stealth investment. Let us start with the S-400 Triumph. Variants of the S-400 can destroy targets at ranges up to 250 miles. That is its maximum kinematic range against a large, non-stealthy target. Against a stealth aircraft, the numbers change dramatically. Despite the growing ability for S-400 air defenses to potentially track and hit stealth aircraft, there is little evidence that such an ability has been verified. In the case of an F-22 or F-35, a surface-to-air missile radar may determine that something is in the area, but lacks the speed, precision, and radar detection to establish a lock on a super high-speed, stealthy 5th-generation aircraft. Number 10, there is the key phrase, establish a lock. Detecting that something might be out there is very different from achieving a weapons-grade radar track. A weapons-grade track means the radar knows the target's position in 3 dimensions, with enough accuracy and update rate to guide a missile to intercept. Against a target with an RCS of 0.0001 square meters, moving at supersonic speed, at high altitude, while potentially employing electronic countermeasures, getting that weapons-grade lock before the aircraft has already released its own weapons is a problem Russia has not solved. As one analysis puts it, the Nebo-M radar used in the S-400 system can detect a stealth fighter from further out using its L-band radar, but about all it can do is detect. Detection is not good enough to attack a stealth aircraft. Now you need that weapons lock, and Russia needs its X-band radars to get that. But they will not get that before missiles and bombs set on destroying the Russian radars are already screaming in. In other words, the S-400 system can detect an incoming stealth aircraft, but it will not achieve a lock until the plane has released its munitions. That is the fundamental problem, and it applies to the S-500 as well. Despite big claims, the S-500 has only seen limited deployment and relatively little verified use in combat. As the war in Ukraine continues and reports appear about Russian air defenses struggling to defend against Western-supplied precision weapons, it is reasonable to question whether the S-500 can perform as Moscow claims. The Prometei may represent the most ambitious air defense system Russia has ever fielded. But its effectiveness in real-world combat against 5th-generation stealth fighters remains theoretical for the most part. Now let us talk about the Nebo-M. This is the system Russia specifically designed to counter stealth, and its approach is actually clever from a physics standpoint. The Nebo-M combines 3 different radar arrays that broadcast on different frequency bands to detect, track, and target low observable aircraft. This system does so by leveraging a largely misunderstood attribute of stealth fighter design, their inherent detectability against lower frequency radar bands. Russia's Nebo-M system uses 2 low-frequency radar arrays, the Nebo-SVU in the VHF band and the Protivnik G in the L band, to detect the presence of stealth fighters as they approach. Here is the physics. VHF radar systems have wavelengths comparable to aircraft feature sizes and should exhibit scattering in the resonance region rather than the optical region, allowing most stealth aircraft to be detected. When the radar wavelength, which ranges from 1 to 10 meters in the VHF band, is close to the size of the aircraft itself, something strange happens. the stealth shaping becomes much less effective. The carefully angled surfaces that deflect X-band waves so beautifully start to resonate, acting almost like tuned antennas, re-radiating energy back toward the radar. At longer wavelengths, the aircraft's dimensions approach or exceed the wavelength, inducing resonant scattering effects that elevate RCS independently of shaping. This resonance arises from currents induced on the target's edges and surfaces, producing backscatter akin to a half-wave dipole, rendering low-frequency returns more akin to non-stealthy targets. So the stealth fighter's RCS at VHF frequencies might jump from 0.0001 square meters to somewhere between 0.1 and 1 square meter. Suddenly it is visible. The Nebo-M can see it. But here's the thing. Seeing it and shooting it down are completely different problems. Despite the advantages offered by VHF radar in detecting stealth aircraft, the longer wavelength results in lower resolution when compared to the size of an X-band radar array. Poor resolution in angle and range has historically prevented these radars from providing accurate targeting and fire control. VHF radar tells you something is out there. It gives you a rough direction and a rough range. But it cannot tell you precisely where the target is within a volume of space several kilometers across. It cannot generate the precise three-dimensional track needed to guide a missile. It is like hearing footsteps in a dark house. You know someone is there. You do not know exactly where. And you definitely cannot throw something and hit them. According to a peer-reviewed assessment published by the Journal of Computations and Modeling in 2014, Russia claims the low-frequency arrays can detect the F-117 at a range of 350 kilometers in an environment free from electronic warfare, and potentially as far as 72 kilometers under heavy jamming. This detection range is the basis for many S-400 counter-stealth claims. But it fails to acknowledge the difference between detecting a stealth fighter and targeting one, and those numbers are for the F-117. The figures represent the detection range for the S-400's low-frequency radars versus the F-117, which offers an RCS approximately 30 times larger than the F-22. As a result, both detection and targeting ranges for more modern fighters will be reduced dramatically. The F-22 is 30 times stealthier than the F-117. 30 times. Apply that to the detection ranges, and the picture gets very grim for Russian planners. Bistatic radar has been proposed as another solution. Instead of having the transmitter and receiver in the same location, you separate them. The transmitter sends out energy, and receivers positioned at different locations pick up the forward scattered energy from the target. Since stealth aircraft are designed to deflect energy away from the transmitter, some of that deflected energy might be picked up by a receiver located elsewhere. In theory, this works. In practice, the engineering challenges are immense. You need precise timing synchronization between transmitter and receiver. You need massive computing power to process the signals. You need the receivers positioned in exactly the right locations relative to the threat axis. And even when everything works perfectly, the detection resolution is often too poor for weapons-grade tracking. The F-22 has flown in combat. It has operated in airspace monitored by Russian radar systems. The aircraft flew over 200 missions over Syria, operating in areas covered by Russian S-400 batteries, deployed to protect assets at Nebo-M Air Base. Either 0 confirmed radar locks, 0 engagements. The F-22 went where it wanted, when it wanted, and the Russian systems watched it happen. Or, more accurately, they did not watch it happen, because they could not see it. Now let us discuss the gap. The technical gap between the F-22 and everything Russia has built to counter it. And more specifically, why Russia cannot close it. Stealth is not one technology. It is not a single material, or a single shape, or a single technique. It is the simultaneous, precise integration of at minimum 15 major engineering disciplines, all working together in harmony. Airframe shaping, edge alignment, surface continuity, ram coating formulation, ram application precision, canopy coating, engine inlet design, exhaust signature management, weapons bay integration, door edge treatment, gap sealing, fastener signature reduction, antenna integration, emissions control, and continuous quality monitoring across the entire aircraft. Every single one of these disciplines must be executed at the highest level. A deficiency in any one of them can compromise the entire system. A poorly sealed panel gap, A coating applied 1 millimeter too thick. A misaligned edge. Any of these can create a radar return that negates the work done everywhere else. The F-22's radar-absorbing coatings, precisely shaped surfaces, and internal weapons bays required manufacturing tolerances far tighter than any previous fighter. The airframe uses more titanium than any other fighter, requiring specialized machining processes. This is why the Su-57 falls short. Russia can design a stealth-shaped airframe. They have done it. The Su-57 has canted vertical tails, blended wing body design, and internal weapons bays. But the execution, the material science, the manufacturing precision, the supply chain required to maintain consistent quality across every subsystem, this is where the gap opens up. Independent assessments estimate the Su-57's RCS to be somewhere between 10 and 100 times higher than the F-22's. That is a massive difference in stealth performance, and it comes down to the accumulated precision of thousands of small engineering details. The United States government spent an estimated $32.4 billion in research and development for the F-22. Procurement cost an additional $34.2 billion, and another $676.6 million went to military construction. When production ended in fiscal year 2010, the total cost was $67.3 billion. $67.3 billion for 195 aircraft. That is the cost of perfection. That is what it takes to build an aircraft that can hide from $40 billion worth of radar. And here's the maintenance reality. When the pilot flies, banking hard can tear or rip the radar-absorbent material. If there are a lot of damages, the aircraft is easier to detect, so maintenance crews try to keep those damages to a minimum. Every flight degrades the stealth coating. Every landing. Every encounter with rain, dust, or temperature extremes. The coatings must be inspected, repaired, and periodically stripped and reapplied. The United States Air Force has launched a major stealth reliability program estimated at around $1.3 billion, aimed at improving the durability of materials and reducing the frequency of major repairs. A billion-dollar program just to make the paint last longer. That tells you everything about the engineering complexity involved. Russia faces a supply chain problem that goes beyond materials science. Many of the specialized materials, manufacturing tools, and quality control systems required for advanced stealth coatings are subject to export controls. The precision required in manufacturing, sub-micron tolerances across enormous surface areas, demands equipment and expertise that Russia has struggled to develop independently, and the economic pressures of recent years have not helped. The F-22 was not built by a single company. The prime contractor, Lockheed Martin, built most of the F-22 airframe and weapon systems and conducted final assembly, while program partner Boeing provided the wings, aft fuselage, avionics integration, and training systems. The supply chain stretched across hundreds of companies, each contributing specialized components manufactured to exact specifications. Replicating that ecosystem is a generational endeavor, and that brings us to the future, because the stealth versus radar contest does not end with the F-22. It is an arms race that has been running since the 1970s, and it is accelerating. The United States Air Force is developing the next-generation air dominance platform, known as NGAD. Details are scarce, deliberately so, but what has been publicly discussed suggests a leap beyond even the F-22 in stealth performance, sensor integration, and combat capability. On the radar side, cognitive radar is emerging. These are systems that use artificial intelligence and machine learning to adaptively change their waveforms, frequencies, and processing algorithms in real time based on the environment they are operating in. Instead of broadcasting a fixed waveform and hoping for a return, cognitive radar analyzes each pulse return and adjusts the next pulse to optimize detection against specific target types. Against a stealth aircraft, a cognitive radar might automatically shift to the frequency band where it detected a momentary anomaly, increasing dwell time and processing gain in that specific direction. Photonic radar is another potential game changer. By using laser-generated microwave signals instead of traditional electronic oscillators, neurophotonic radar can achieve much wider instantaneous bandwidth with lower noise. In theory, this could improve range resolution to the point where even small radar returns could be extracted from the noise floor. But here is the pattern that has held for 50 years. Every time radar makes an advance, stealth engineering responds with a counter-advance. And the stealth counter-advance has consistently stayed one step ahead. New materials absorb wider frequency ranges. New shapes scatter energy more effectively. New coatings are more durable and require less maintenance. The cycle continues. Additional upgrades being tested on the F-22 include new sensors and antennas, integration of new weapons, including the AIM-260 Joint Advanced Tactical Missile, and reliability improvements such as more durable stealth coatings. And other developments include all-aspect infrared search and track functionality, and manned-unmanned teaming capability with uncrewed collaborative combat aircraft. The F-22 itself is still being upgraded. It is getting new weapons, new coatings, new sensors. An aircraft that entered service in 2005 is still being refined, still being improved, still being pushed closer to the physical limits of what is detectable. And that is perhaps the most remarkable thing about this story. The F-22 was designed in the 1980s. It was built in the 1990s. It has been flying combat missions for 2 decades. And no adversary radar system has publicly demonstrated the ability to reliably track and engage it. That brings us back to where we started. $40 billion. What did Russia buy with that money? Then they bought an air defense network that can track conventional aircraft with extraordinary precision. They bought systems that can detect that something stealthy might be approaching from a general direction. They bought radars that can see the F-22 on VHF frequencies, but cannot guide a missile to hit it. They bought detection without engagement, awareness without action. The ability to know something is coming without the ability to stop it. In practical application, stealth is not about preventing detection altogether, but rather delaying it for long enough for the fighter aircraft to either strike first or escape a potential threat. And the F-22 delays detection so effectively that by the time Russian radar achieves anything approaching a track, the missiles are already in the air, and the Raptor is already turning for home. That is the engineering reality, not propaganda, not theory, physics. A $67 billion aircraft program defeated a $40 billion radar network, not with brute force, not with overwhelming numbers, but with geometry, material science, and an obsessive attention to detail that extends down to the radar return of a hinge. The arms race between stealth and radar is the longest-running engineering competition in military history. Each side pushes the other to innovate. Each breakthrough forces a response. And somewhere right now, in a classified laboratory that does not officially exist, engineers on both sides are working on the next generation of this contest. But for the moment, the scoreboard is clear. Russia built the wall, America built the ghost. And the ghost walked right through. If this breakdown changed how you think about stealth technology, or if you want to see us go even deeper on specific systems like the NGAD, the B-21 Raider, or the future of electronic warfare, subscribe to Weapons Lab and hit the notification bell. We drop one deep dive military engineering breakdown every week. Share this with someone who thinks radar can see everything. And if you have a topic you want us to cover next, put it in the comments. Because in the end, the race between the signal and the silence will define the next century of air warfare. And right now, the silence is winning.